So this condensation and hydrolysis reaction. So this condensation and hydrolysis reaction works no matter what the molecules are. It works no matter what the starting molecules are. This could be an amino acid glycine and lysine. It could be the glycerol and the fatty acid. It doesn't matter. Condensation reaction to form a bond and hydrolysis reaction to break a bond by the addition or subtraction, the reverse respectively, of water. So the removal of water to form a bond and the addition of water to break a bond, this is true no matter what molecule you are dealing with. So possibly helpful terminology, by which I mean absolutely useful terminology, conformational isomers. So when we're talking about carbohydrates, we have our chair form of glucose, because it looks like a lawn chair. We have our boat form, which is an unstable intermediate form, because it looks like a boat, or some organic chemist thought it did anyway. I'm not sure quite what they were thinking, but okay. And then that results in, this can flip down, and we'll have the reverse of the chair form. It's the chair form all over again on the other side. No bonds have changed. No bonds have been broken. No bonds have been reformed. No electrons have moved around. No shares of electrons. No pairs of electrons shared. No pairs of electrons have been shared in any way. This is just the movement in bonds that already exist. This is just the interplay between bonds. So conformational isomerism are isomers, the same molecule that takes on different shapes because it can conform to fit a different shape. You can just fold it. Click, 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 click. You just move them. Now, naming of carbohydrates, we have a very simple naming scheme. It's based on Greek. We have how many carbons? How many carbons does it have? If there are 3 carbons, it's tritose. If there are 4 carbons, it is quadrose. If it is 5 carbons, it is pentose. If it is 6 carbons, it is hexose. 7, septose, etc., etc., etc. So on and so forth with the Greek name, all the way to dodecatose. All right? Oh, sorry, tetros, not quadros. Quad would be Latin. All right? So pentose, keep this one in mind. This is ribose. This is ribose, which is going to be useful for RNA. We have these 2 forms. We have the chain form and the ring form. The chain form is the form where we have our aldehyde group or our ketone group as required. And in the ring form, we have a ring. It is more chemically active in the chain form. In solution, sugar will often become the chain form, and that is how it exists and persists in an aqueous solution. So this is our hexose sugar. This is D-glucose, dextroglucose. Dextrose, for short. It consists of 6 carbons with an aldehyde group at the 1 carbon, a hydroxyl group on the right side, if you're doing it that way, on the 2 carbon, on the left on the 3 carbon, right 4, right 5, and our CH2OH, our end hydroxyl group on our 6th carbon. That carbon can rotate, so it doesn't matter where that one is. Now, we are numbering our carbons. In our ring form, we have a 1,5 ether linkage. this one carbon, this double bonded oxygen, will become our ether link. It will bond to our 5 carbon, the hydroxyl group in the 5 carbon position, to form our ether link. So this is what determines the ring structure. Where is that double bonded oxygen? Where is that double bond? We are numbering these carbons based on what's the most interesting group near the end. So this is our 1, 2, 3, 4, 5, 6. Remember where they are. This is a 1,5 ether linkage because it is the 1 and the 5 carbon, and it is an ether. Carbon, oxygen, carbon. Now, this must be committed to memory. The Fischer projection and ring form structures of glucose, galactose, and fructose. They differ in a few changes, and that is all. Glucose versus galactose in the projection, the Fischer projection, has on the 4th carbon, the hydroxyl group is on the right, and in galactose, the hydroxyl group is on the left. In fructose, it is the same as glucose, only you have switched. You have switched where the double bonded oxygen is. It is, instead of on the end as an aldehyde group, it is now on the 2 carbon as a ketone. So that makes this an aldose sugar, and a ketose sugar, based on the group of where that double bonded oxygen is. Aldehyde, aldehyde, ketone. In the ring form, glucose and galactose look very much the same. The difference being that the 4 carbon of galactose, the hydroxyl group on the 4 carbon points up versus is trans configuration, which is up when the 1 carbon hydroxyl group is down. They are opposed to one another. They are in the trans configuration. The glucose will be with both hydroxyl groups down. This will be our alpha glucose. Now, any other further differences? There really aren't. In our fructose form, by the way, this is forming a 5-sided ring, but not a 5 carbon. It is not a pentose sugar. It is still a hexose sugar because we have 1, 2, 3, 4, 5, 6 carbons. And our CH2OH groups are in a trans configuration to one another. Now, aldose and ketose, which I mentioned before, the carbon-oxygen double bond is located at the end of the carbon chain in an aldose sugar. In a ketose sugar, the carbon-oxygen double bond is located within the interior of the carbon chain. So, glycosidic bonds. A glycosidic bond is where we have, or a glycogen bond, or a glycosidic linkage. That is where we have a condensation reaction where water is condensed out, and this forms the carbon-oxygen-carbon linkage, glycosidic linkage between these 2 molecules. This is a 1,4 glycosidic linkage. It is a 1,4 glycosidic linkage because it is on the carbon 1 of the first glucose, and it is on the carbon 4 of the second glucose. Glucose plus glucose yields maltose. Alpha glucose plus alpha glucose yields maltose. So now we have an idea of our simple carbohydrates. Monosaccharides, like glucose, are just 1 carbohydrate unit. A disaccharide, like sucrose, is 2 monosaccharides bound together by a glycogen bond. So we have glucose and fructose here connected by a glycosidic bond. That becomes a disaccharide. Complex carbohydrates is a polysaccharide. A polysaccharide is when you have more than 2 monosaccharides bound together. Mono, di, poly. One, two, many. Now, remember that in our carbohydrate molecule, our empirical formula, or our molecular formula, was C6H12O6. In a disaccharide, where you are adding two monosaccharides together, you would think perhaps that it would be C6 plus H12O6, and you would just add them together, right? Wrong. That's forgetting that you are, in fact, subtracting water for the condensation reaction. So, C12, H24 minus 2 is 22. O12, 6 plus 6, minus 1 is 11. So a disaccharide's chemical formula, no matter whether it is glucose plus galactose, galactose plus fructose, fructose plus fructose, doesn't matter. It will be C12H22O11. Further additions of monosaccharides will always subtract water. It will add C6H12O6 and subtract H2O. So, that is how we move forward and add in the chemical formula department. So, here's our table of the different combinations of monosaccharides. When glucose and glucose get together, and they are both the alpha glucose in an alpha 1,4 glycosidic linkage, that becomes maltose. Beta 1,4 glycosidic linkage will be cellobiose. Cellobiose is a breakdown product of cellulose, which is a chain of beta glucose. Beta glucose looks a lot like galactose, but it's not. So we'll get to that in a second. Glucose plus fructose is sucrose. Excuse me. And that has an alpha 1 beta 2 glycosidic bond. Because glucose is in the alpha configuration, and fructose, excuse me, is in the beta configuration, and it bonds the 1 carbon of the glucose to the 2 carbon of the fructose. So sucrose is alpha 1 2 beta sucrose. So glucose to fructose, galactose to glucose gets you lactose. That is a beta 1,4 glycosidic bond. A beta 1,4 glycosidic bond. Glucose must be in the beta configuration. Galactose will be in any 4-carbon configuration. So, it's the same over there, glucose to galactose. Fructose plus galactose gets you lactulose. That is also in a beta 1,4 configuration, where fructose is in the beta configuration and galactose is in the 4 configuration. So, maltose is sugar, is a malt sugar, so a malt beverage, for example. Cellobiose is a breakdown product of cellulose, so what you would get when a rabbit is trying to digest its meal. Sucrose is table sugar, lactose is milk sugar, and lactulose is a diuretic, as in it makes you poop, like really badly, like a lot. So, table sugar, milk sugar, malt sugar, lactulose is used to treat constipation and hepatic encephalopathy because it is not absorbed. Cellobiose is a hydrolysis product of cellulose. Cellulose is the primary structural polysaccharide in many plants. We'll get there. So, alpha versus beta for glucose. So, here is alpha glucose. Here is beta glucose. The 4-carbon is always the same. The 4-carbon will always have its hydroxyl group down. That is, in fact, the difference between alpha glucose and alpha galactose. The 4-carbon in alpha glucose, the 4-carbon in galactose is flipped. In alpha glucose, it is down, and 1 is down. In beta glucose, the 4-carbon, the hydroxyl group is down, and the 1-carbon, the hydroxyl group is up. How did this happen? Because the aldehyde group can turn. Because the aldehyde group can rotate, if it rotates to the other side when it forms that ring structure, then the hydroxyl group will be upside down versus right side down. Will be right side up, upside up versus upside down. So, in your chair form, alpha glucose will have hydroxyl group there, hydroxyl group there. Beta glucose will have hydroxyl group there, hydroxyl group there. Why does this matter? This matters because in beta glucose monomers, in order for any glucose to bind to other glucose, and I'm going to draw this way. In order for any glucose to bond to any other glucose, this will be alpha glucose, by the way. Both hydroxyl groups must be facing each other. They can't face away from each other. They can't be on opposite sides. If you have an alpha glucose and a beta glucose, for example, if this is your beta glucose, you're not going to get that interaction. There's too much distance between those hydroxyl groups. You need to have the hydroxyl groups be facing right next to each other for that interaction to happen. They have to be touching. They have to be in the same plane of orientation. They must be in the same plane of orientation. So, for alpha glucose, this is fine. They can all be in the same orientation, and it's fine. In fact, that's how you get amylose, an unbranched chain of alpha glucose, alpha 1,4 glycosidic bonds. This one bonds to this one, which bonds to this one, which bonds to this one. Just continuing forward until you're done. But in beta, so we have beta glucose, and here we'll have our 4-carbon and our there. So we'll have hydroxyl group up versus hydrogen down. All right. In order for this to bond to another molecule, you have to flip the other molecule upside down. Flipping it all the way upside down. And then the next one can be flipped right side up. Oops, that looks terrible. Let's fix that. You have to flip 180 degrees. They have to be flipped 180 degrees in order for these hydroxyl groups to interact at all. That's why it matters That's why it matters whether you have a hydroxyl group at the 1 carbon be up or down compared to the 4 carbon. Because if you didn't, you wouldn't. If you had them down compared to each other, you could just chain them together and it'd be fine. Every so often, with the alpha 1,4 glycosidic bond, the hydroxyl groups that are down here will interact with each other and they'll polarize and they will have a hydrogen bonding that causes them to curve into a solenoid, and you'll have this slinky pattern form. That's a solenoid. But with beta glucose, these hydroxyl groups are 180 degree flipped from each other every time. So they will not interact. So they will zigzag and scatter into a perfectly straight line. So you get this fiber that is cellulose. Thus, fiber in your diet. That's why green leafy vegetables give you fiber, because the primary component in plants is cellulose, fiber. So, which brings us to the idea of the polysaccharide as an energy storage molecule. Alpha glucose is readily usable by animals as an energy source, as a source of fuel to produce energy for the production of ATP, excuse me. Starch. Starch is the energy storage in plants, and glycogen is the animal version of starch. It is energy storage in animals. Amylose is a straight, unbranched chain of alpha glucose. Unbroken 1,4 alpha 1,4 glycosidic bond, alpha 1,4 glycosidic bond, alpha 1,4 glycosidic bond, continuing on in perpetuity until, well, you're done. Amylopectin, however, is a firm texture. It is a starch that has branches. These branches occur at the 6 carbon, which is up here. So these 6 carbons, they are a 1,6, an alpha 1,6 glycosidic bond. So they will branch like so, and continue on with further 1,4 glycosidic bonds. So at the 6 carbon, you will have a 1,6 glycosidic